another dollar. Today I'm doing an Atcoder regular contest. 127. Starts in 30 seconds. And then I'm listening to microtonal lo-fi hip-hop. So, yeah. That's what I felt like listening today. Let's get everything ready. Alright. Hopefully I don't fail. Though I always fail. And then, and 4, 3, 2, 1. Okay, and time to start. And then today, I am not starting super late, which is good, because there's a Code Forces contest tomorrow morning, so I need to wake up early for that. Alright, I have an integer x, f of x be the number of leading zeros, leading ones. Okay, and then we find 1 plus f, 2 plus blah blah. Okay. So basically, we can just say, what's the number of numbers with 1 leading 1, what's the number of numbers with 2 leading ones, etc. Okay, that seems easy enough. So let's just input n, then we'll iterate over the number of leading ones. And I is equal to, let's just say 1. Less than j is less than or equal to n I plus plus j is equal to 10 times j plus 1, something like this. Oh, obviously these will need to be long ones. Alright, let's see. So now we need to say what do we need to do now? What are we gonna do? We should iterate over both the length of the number and the number of ones. Right. Iterate over. Okay, like, there's my. We want to iterate over how long the number is and how many ones are at the front. And then from there, we say then let's say we fix the length of the number of ones. How do we count how many of left is less than n? Well, we know that if anywhere over here is like so if the number is less than n, then obviously it's already good. Okay, it's actually easier to think of it as an array. So think of the number n as an array with each number between 1 and 10. If we have a point anywhere that they have the same value, that they have that our number that we're iterating over has less than the array n, then everything after it can be anything we want. So it'd just be like 10 to the number of spaces left. However, if the whole thing is equal to a prefix of n, then we know that this number can be up to the number of same number that corresponds to the prefix of n. Lastly, there's some number over here, such that here is a position of n, is less than our array A, then we know that there are no solutions. So let's just like do that, I guess. Let's make a const 16. So let's turn our number n into m. Then we say first we do 0 n plus we have I is equal to n% 10. Something like this. Now we say this is 0. We'll iterate over the length. And then the number of zeros. The number of ones at the beginning. And now we say, now we need to see if the prefix is the same, less, or greater. So then we do for A is equal to n minus 1. I is going to equal to greater than I minus j. No. Greater than or equal to I minus j. We have 1, 1. We have to go to position. L1 is minus. Let's let an integer let's go 1. Let's say it's this. Then we'll let the n do right. This is x. So we're gonna iterate backwards from the beginning. And we say to I minus j, and we have L is greater than L is greater than I, 1, 0. If we have L is greater than L is greater than I question mark 0 4 1. A of L is less than if so here we break it's less than now we do 4. L is equal to I minus 3 plus 1. L is L minus. Now we do x times equals y question mark n A of L equals Hopefully I did this right. Well, that's definitely not right. J. One. Oh, I must be doing this opposite somehow. This is what's less here. This one's greater. Four. Okay, this looks right. Let's get this. And then hopefully this one's right too. Yep. Easy clap. Alright, hopefully be right and I didn't mess anything up. That would be preferable. What? How? What? Sample 2. Sample 2. 120. Where am I messing up here? 26. Oh, wait. Should be x times j. Right, because j is the number of zeros. Oops, that's my bad. 30, huh? Still wrong. How? Okay, well now it's getting this wrong. Does it get this right then? Why is it getting 5? Alright, 1 with 1 That should get 1 times 1. 2 times 1. 1, 0. We have to make sure that the we're over counting because we're counting the times when there's like 2 ones twice. Then I don't get why what we were doing before doesn't work. Why am I taking so long on this? Hold on. Because this will count the 1, 11 here, and 11 here. Oh, right. You still have to iterate then over how far up is the... Okay. Let me... So you have to iterate how far up the prefix then it has in common. Like, and then the rest you can do whatever you want. Okay. So what am I gonna do? How am I gonna code it? So we need like what? L is less than or equal to. L is less than or equal to what? Saying. What is it? If y. So this is true. Equal to 0. Equal to I minus 2. 1. Oh, what am I doing with this? This can just be. Need to iterate how much I have in common. Or P 0 P is less than L plus Z times equals 10. Say if not x, x else. Alright, let's say if not x, what does that mean? That means we have to deal with iterating what we have in common. Otherwise, we already know it's less. We can just do here we have to iterate over. One. Is less than I minus 3. P is less than L, Z times equals 10. And then Z times equals what? A of L has to be less than 8 though. Something like this, I think. Did I do this right? Hopefully. Okay. This wasn't exactly the best way to code it, but you know, it gets the job done. Yeah. Okay, AC. I don't really like problems like that, where you just have to like iterate. In general, I don't like a digit iterating or digit DP. Those are all kind of like casework and not usually very interesting. But I don't know, every once in a while they surprise me. Given n and l, find a tuple of 3 n strings, satisfies the following. Si is a string of length l consisting of 0, 1, 2. All SI are pairwise distinct, and for exactly n of the strings, so the jth character is C. T for this tuples. Okay, that's kind of confusing wording. It says 3 n strings, exactly n of the strings, the jth character is C. Okay. Basically, you have a bunch of strings 0, 1, 2 like this. You say, for each, think about each of the strings as like an array, where each position has 0, 1, or 2. So this is like for n equals 2, because there are 3 times 2, which equals to 6 strings. And then you're gonna say there are exactly n strings such that the jth character is C. That means we'll have to do like 0, 0, 1, 1, 2, 2. And then we want to eventually make T for the tuple be the lexicographically smallest string possible. Well then, I think it's not hard to see. As far as we can, we want to like put the minimal character with the maximal ones, right? 2, 2. Something like this. Because then only these strings would be in contention as the maximal. However, we have to make sure all the strings are pairwise distinct, right? So let's think about that like this. So first, on the first character, we'll have to have 0, 0, 1, 1, 2, 2, right? After that, it doesn't matter what we put in any of these strings, because they'll always be lexicographically less. Now, let's see how far forward on the 2 strings we can just put 0, 0s and still have room to make all of them at the end lexicographically pairwise distinct. Now, how do we make them all? How do we make sure they're pairwise distinct at the end? and are as small as lexicographically possible. So the problem becomes, given integers 0, 1, 2, and because we don't care about the characters we place in any of these spots at the end, we can take whatever we put on the two strings and then just shift them all the characters by like 1 modulo 3 and place them in these positions. That would ensure, because that would make sure these are pairwise distinct, that would also mean each of these groups are pairwise distinct. So all we have to do is think about the 2 case, and then it's easy to solve from there. So how can we put the, and here we're allowed to put, and we have no restriction anymore that there are n characters of each type. Why? Because any character we put here, we can just put over here. Wait, is that true? Hold on, let me think. Imagine we put in one position 2 zeros, and we get 2 1s, 2 2s. We put a 0 1. Yeah. I think we can just place the characters however we want, as long as the strings are pairwise distinct. 3n is less than or equal to 3 to the l. Okay, that just makes sure they can all be pairwise distinct. So the end of the strings, to be pairwise distinct, they'll all have to be like just values of in base 3. So 0, 0, 0, 1. Now we can just take all of these, base 3, shift them like by 1, and go 1, 1, 1, 1, 1, 1, 1, 1, 2, and 2, 2, 2, 2, 2. 2, 2, 2, 2, 3, 0. That will ensure the lexicographically largest is as small as possible, and each character should be n times at each position. I think that's all correct. Okay, that seems really easy. Hopefully I didn't mess that up. Well, let me code it. I think it'll make more sense once I code it. Okay. Max is equal to 2. I don't really need to store anything, I guess, right? Okay. How do we just do 4, 0, plus 3 times add x plus. So first we'll print out the first character, which will be I over n, 2, plus the first ones, plus. Here's where we print out like the values base 3, but then shifted. So we need to print these out. I guess it's easiest just to make an array. Let's make it all N, 0. This 1 x I is n, j is less than k, j is plus, j is 1, okay. A of j. A of j is equal to x percent 3 x 3 wait, hold on. Percent 3 Can I just print the values in base? No, I can't do that. I can do x percent 3 x plus I plus 1 percent 3. Now we do 0. This should be 1. Let's do it. Okay. And let's see. Did we do this right? Who knows? Alright. 0, 1, 0, 0. Oh, what do we do wrong? X plus x plus I plus 0. 2, 0. Okay, I think this is right. Okay, that was easy. That was easier than A. Oh yeah, let's look at the standings. Show standings. Probably everyone basically solved the same so far, because they were both really easy. Now Snook has written on the blackboard every integer from 1 to 2 to the n minus 1. Find the x lexicographically smallest string when seeing the integers on the blackboard as strings. Okay. Oh, I see. So you can see that the numbers, because you're not counting the leading zeros, the binary representation in lexicographical order isn't exactly the same as like the number order. But I think this is easy, and we can just do binary search. Right. Wait. Oh wait. That's like binary searching over 2 to the... Well, it'd be like 10 to the 6th position, I guess. lexicographically large string. Okay. Okay. Everyone solved A and B, and I took forever on A. Basically, we want to iterate from okay. We need to iterate from front to back and say, given this prefix, how many numbers are there that are left? Well, given the prefix, how many numbers have we counted? Put a 1 down. How many numbers remaining are there that are less, lexicographically less? Okay, I think it's easier to fix the size of the array to be n. For a 1, we say, let's say we put a 1 here. How many numbers are there left that are lexicographically less? I'm putting a 1 here. And we can imagine, for all numbers with leading zeros, we instead just like put them at the end, basically. Well, alright, we'd have to do the number. Let's start here. We're gonna say there has to be a 1 in the first position. Okay. Basically, we're gonna do a DP going backwards, where for like a position I, DP of I, for 0 and 1, is the number of numbers left when you put a 0 here that are lexicographically less than whatever prefix you have up to here. So how it works is we do dp of I j is equal to like a p of I plus 1, 0, plus dp I plus 1, 1, plus, because you could have either a 0 or 1 there, and then plus 1, because you can also have the place where you just end it here. Do I even need to do this? Oh well, let's just do that. There's probably a math formula where you can get dp of ij, but oh well. I'll just compute it ahead of time with easy dp. Wait, x is in binary. Oh, that makes it even worse. Shoot. Never mind, we can't do this. Because x can be very large, so we can't just like store the dp value. Let's see. Let's try this. I'm gonna write all the numbers for this case, for 3, and with their like number order mapped to their lexicographical order. So you'll see it's like 0, 0, 0, 0, 0, 1, 0, 0, 2. Oh wait, oops. 0, 1, 0. And then I'm gonna try to create like a bijection between them. 0, 0. What? I'm writing too big. Alright, we need to not write that big. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Let's just do this. 1, 0, 0, 1, 0, 1, and 1, 1, 1. Now their lexicographical order is 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0. 1, 0, 1, 0, 1, 1, 1, 1, 1. Alright, do we see some sort of pattern about how to go from here to here? I'm not seeing a pattern immediately. Oh, oops, why is my laptop not charging? Okay. How much time do we have? An hour 15 minutes. Okay. Hopefully we can finish this in 15 minutes. let's just like think about the DP, I guess. So there'd be like 1, 1, 2, 3, 3. Of course the numbers are the same, right? 26, 7. Oh wait, 14. Oh, okay. That makes it easier. What do we notice about this? So remember that DP idea? Well, we can see they're just the powers of 2 minus 1. So basically, we put the first index as a 1, because it has to be 1. And we say, is k equal to, I guess, 0? Is k greater than 1? So we subtract 1 from k. Is k greater than 2? Alright, so on the number x, we would need to do 2 operations. Subtract 1, right, and subtract 2 to the k minus 1. But if we do it like naively, that'll be too slow, right? And it'll be O(n) squared. So I don't think we can do that. Can you? Well, maybe you can prove it's like amortized. It will work out. Like, it's well known, a binary counter. If you add 1, like n times, well, but that, I don't think that really applies here. Well, I think subtracting 1 isn't bad. It's only when you subtract 2 to the n minus 1. Well, that's like adding 2 to the n and subtracting 1. I don't know. Maybe it somehow works. I want to think more, though, about a pattern. And here. First we see it's the ones with 1 bit, and then the 0. And it's the ones with 2 bits. Wait, am I missing a number? 1, 2, 3, 4, 5. Oh, I am. Forgot. What did I forget? This one should be 111. This one should be 110. Hard to find a pattern when you write the numbers wrong. Then 1, 0, 1, 0, 0, 0, 1, 1, 1. 1, 1, 0. So what do we notice about this? Well, all the numbers with one bit set come before the ones with 2 bits, then 3 bits. But is that always true? 0, 1, 1, 1 come before 1, 1, 1. So no. Yeah, I'm not too sure. Maybe you just can, like, do, like, addition and stuff on X. And it'll amortize to ON. I think that's probably the case, to be honest. Alright, let me look at the next problem. How many people have solved it? I'll look at the next problem and then see if just doing the operations on X will work in amortized time. But what about testing if like k is less than 2 to the k minus 1? Don't we have to do that in like a one time? Well, okay, it should be pretty easy. We just keep the length and the number of bits set, I guess. Given are sequences of n integers each, a and b, and then we want to find the sum of the minimum for each pair of indices, aix or aj, or bix or bj. Well, I like that problem more than this, so let me think about that a bit. Let me think about this. So for each pair, we look like 1 and 2. It's AI, X or A1, X or A2, or B1, X or B2 less. Alright, well the first thing is, how do we get the sum of all XORs, right? Well, it's just like how many bits have a 0 and how many bits have 1. And we add like the combinations. So dealing with a min, think about A1 XOR AI XOR BI. XOR AJ XOR BJ. Now, if the kth bit is 0, that means the two pairs XOR to the same value at that bit. So we have to, otherwise we can pick which one is smaller. There's only that pair or something like that. So we'd say, so in the AI and BI, we could for each bit from think of a binary number or whatever, iterate from the top bit going downward. Then we split them into two groups based on all the ones that have AI and BI have a 1 at the top and that have a 0 at the top. And then we calculate these two groups separately, the pairs between them. Then the final question becomes, how do we get the number of pairs between these two groups? Well, each of these will have AI XOR BI equal 1 and AJ XOR BJ equals 0. So between here, we should always either be able to get what? Wait, hold on. Well, 1, 0, and 1, 0. 1 XOR 1 is 0, and 0 XOR 0 is 0, so that doesn't really help, I guess. How do we know if they can XOR to different values then? Well, one of them would have to be 1, 0, and the other one would have to be 0, 0, 1, 1. So 1, 0. Okay, I'm not really having ideas. I'm gonna try coding C. Sorry, I'm just I don't know. I'm not in the mindset today for this. It should be. We need a counter, which is the number of ones. This is saying like we subtract the ith bit, we subtract like 2 to the x, or add 2 to the x. And we're gonna hope that the amortized over all operations is 1. Is 4. S. S minus equals 0. A plus S. See out 1. Then we just do no. Why would just do? Yeah, this is what I want. Comma. S plus equal. N size 0. I'd prefer. No. It's better if it does that. Yes. If. Now we say can we put a 1 here and continue? That would need oh wait. We only need the subtract. Because either we're subtracting 1 or we're subtracting 2 to the n. If as that size, equal to 2. Is greater than I. This one is t subtract 0, 0, else I think this is basically what we do. I'll make it all into okay. I don't know how to prove it, but I'm guessing because we're only subtracting powers of 2, it'll be similar to like a binary counter argument, where you can say the amortized of all the subtractions is O(n), even though a single subtraction is O(n), something like that. We'll see. Hopefully it works out. While not s of x, s equals 1, x is equal to 0, while s dot back, s dot back, s dot up. Okay, that was actually a really short code. Well, let's see if it gives the right answer. And it did that. Why? Let's see where it goes wrong. Oh wait, we don't even need k anymore either. K is useless. Now let's say, well, not x. I'm gonna keep it as a string actually, because I want to be able to print it out. I guess if x 0. Something like this. Wait, oh. Should be x was. Also, let's use a for loop instead. For. Not the n. Okay. I like it like this. 1, 0. Why did we put 1, 0 instead of 1, 1? Let's see how it works. Oh, okay, now it's working. No. No, it's not working. Oh, I see. See it. Yes. So S goes to 1. So we're taking out 1, 2, 3, 4 possibilities. Supposed to be like this. would be 2 to the n minus 1 here. There's the option of stopping. And then there's also we know that we always have to put it 2. At the beginning, you have to put a 2. You have to put a 1. I think we have to do it like this. What are we getting? After we subtract 0, we're getting 2 to this. Now we're subtracting here. Getting this. What am I doing wrong? Getting 1, 1, 1. After the first one, we have n minus 2 choices. We can either let's think about how it's supposed to work. Put down a 1. After we put down a 1, how many choices are there? That you put down nothing after it. There's 1. And there's how many choices where there's a 0 after? 1, 2, 3, 2 to the minus 1. So we say if this is greater than or equal to 2 to the I, 4, 3 minus 1 is 2. I guess it should be like this then. Does this work? What is it? Oh, it looks like it's working maybe. Alright, let's try it. Hopefully it works. The problem, of course, is this might be ON, but nope, it worked just fine. 60 millisecond. How do you prove this is amortized ON? So obviously if you have like a long chain of zeros, then they all become ones. Oh no. I'm bad at amortized analysis, but I'm good at amortized guess out. Oh well. Alright. I guess that was kinda interesting. I enjoy. There aren't too many amortized problems in CP, so it's nice to see a few. D and E. Let's read E. There's also F. Let's read E just for fun, though I doubt it will be easier than D. Alright, so let's first just set up code here. Given is a sequence of a plus b integers. Okay, a1s and b2s. Stuke has a set S. He's going to do a plus b operations. A plus b integers. A1s, B2s, plus B operations, choose an integer V and add it to S. Delete from S the element with the largest value. How many sets can there be in the final state of S? What is the sequence of a plus b integers for? Oh, wait. The operation is dependent on x. I'm dumb. Just integer, add it to s. Else delete from s the largest value. I see. How many sets could be the final state? Okay. We got this done. We don't need to think about this stuff up here. So let me give you an example of this. So let's say you have the operations. 1, 2, 1, 1, 2, 1. So let's pick numbers. A is 4 and B is 2 then, right? Let's pick numbers for each of the ones. So here we'll put in 3, 2, 5, 3, 2, 4, 4. And let's look at the set S after the operations. First S is empty, and then we add 3, but in the 2 we get rid of the 2, so it's empty again. Then we add the 2, and we add the 4, but we delete, the largest element of S, which is 4, and the 2. Then we add a 3. So 2, 3 is a possible set. And we're trying to figure out the possible n values of the set. We know A is less than or equal to 5,000. Think about it in reverse. For each one, we can delete any element, and for each 2, we have to add the greatest element, right? And from that, we have to be able to get to a null set. Delete any element, or add an element greater than all of the set. I'm not sure. I'll go back to thinking about D. Both D and E look pretty hard. So for D, this was the XOR button. Min of AI XOR BJ. BI XOR BJ. Well, let's think about fixing one of the indices. So like we fix I, and then we get the sum for all j using like a data structure or something. So what kind of data structure can we use? Well, is there like, first off, is there like some alternate definition of min? Min. Map. It does not look like anything I'm looking for. Minimum. It's gonna give derivative. It's not what I want. Okay. Okay, there's nothing related to what I want. Which I didn't expect. Okay. For a fixed AI BI pair. So we'll say, let's say we're just looking at A1, B1, right? What's a data structure that can get the answer with that and all other pairs? Well, we know say that we know for any other pair of AJ, BJ, if they have like the same or flipped, then we don't know whether they're minimum or maximum yet, which is minimum or maximum for that bit. So we can just like add the answer, whatever. So basically, we know that 1, 0 and 0, 1 are the same, or 1, 1 and 0, 0 are not. Once we have a 1, 1, 0, 0, just add all those to the answer. How much time? 30 days. Need to think of ideas. 2 to the 18. That's kind of small, I guess. I mean, it's around 10 to the 5th, I think. Well, it should be around the same as n. Yeah. AI XOR AJ. Alright, imagine we had like imagine we had like a try based on if the bits are the same, like the 1 and 0 is the same or different. And now in that try, here's a same, different. Now, what does each node store? It stores for all the same in the subtree. Oh, what is the number? For the ones that are like well, basically, it stores for every pair, like 1, 0, 0, 1. What are the number of bits of for both A and B afterwards? Right? All we need to do is store that for every pair. I think that's really all there is, actually. If we store that in a data structure, we just keep going down like the ones that match our current one, and then for the different pairs, we like add all the answers in the subtree. Yeah, I guess that's it. Okay, that seems pretty simple, actually. Hopefully you'll see what I mean in that code. Don't look like too many people in D. Alright, this is a bit challenging. 18. So basically I'm creating a trie, which is, the trie is basically made out of AI, X, or BI, but at each node we're storing information about all the pairs AI, J at that node. Well, no, hopefully that. We'll see, so it's like, this should be max M. 2. Maximum. Okay, there's no way that fits in memory bounds. But I kind of need all that memory. Oh wait, 1024 megabytes? Okay, yeah, that's a lot of memory. Hopefully it'll work. Alright, let's go to CNN. Nixon. Alright, first we see an A and B. Now we iterate here. First we query the data structure, then we need to add to the data structure. So we set like 0. So query, and then alright, let's see. This one. J, so J minus. Is that an extra? Yeah, minus. Okay, this just makes it so y is equal to I and y equal to tr. X I J 1 if not y. X is equal to we should be able to both add to the answer and query as we're going down this section. x is equal to y. Okay, we need to add the answers. So let's see. So first, let's add the answer. Q equals y plus y plus y. Px. We'll just do L0, plus. Equals f of what? L? XOR. Should be max L. This is J. F of, right, X. L. L. XL P P XOR y get rid of D and just say bx equals a. A of I XOR P. Should be like this. C is a B of I. Let's let this go. Y Z Z. Now we do f of x f x l. Okay, never mind. I'm adding back d. E of I plus plus. Zero. This equals A of I first off. This is x, j, x, j, not A of I. Y, L, 1 is equal to easy. This equals y xl. CC. What? This is something like this. Equal to x a of I x y b of I. Okay. And now we do this. Alright. That's a lot of stuff. This equals should be it. Well, I have no clue if this is gonna work, but here's my try. How much time do I have? 9 minutes. Can I get this in time? We're not gonna get E in time, that's for sure. What is happening? Okay, yeah. We're just gonna change this to max end. So there's no way this is gonna fit in time. Wow, that worked great. Alright, not too sure what I'm doing wrong. Let's change K to be smaller for now. Plus, well, that's not good. How is it even getting this? Let's see how right every time. Let's see where it goes wrong. Alright, how is it getting anything on the first value? x xj not y not z. Alright, so it's getting values even just from this. How? xj not y not z. C out of xj not y not z. Huh? Not y not z. Oh, let's do 0. I see. Well, it's better than before at least. Alright, what is the max? 1x or 2 is 3. 4x or 5 is 1. Wait, it's supposed to be the minimum? What it should be. 2. Okay, I guess that's closer. 1, 2, 0, 1, 2. Why is it not getting this right? Is it forgetting to put this in? Zero is A, 1 is B, Y, X, or P. Why are we doing that? It's 1. So this should just be Y squared. See? This should be also Y. sure if that worked out as I wanted. Not the right answer though. No, they did not. You can see that the problem is that after the second time, rec should be 1, but it's 0. Why is that? I'm not gonna finish in time. Oh, I think my idea was right. I'm pretty sure my idea was right. Should I try to fix it? 35 seconds. Why? What am I doing wrong? What am I doing wrong? Who else got D? Yeah, a decent amount of people got D. We should have been able to get it. Well, I think my idea is right of doing a try based on like AIX or BI, and then taking these sums. I just messed up with the casework. Maybe I'll try a little bit longer to see where I went wrong. Alright, first off, we know what bit is different. Here's the problem. Wait, never mind. Let's go to 1, 2, 3, 4, 5, 3, 6, 7. So on 3, it should be getting the pair with 1, right? Has 0, 1, 0, 1. Oh yeah, let's look at it before the what's the first node that they're different? Should be node 2. No, node 3. 3 is 1, 0. Or this is 0, 0. So we know at that point, you should be able to get the sum of the other one. So we know that x, which is 3, we have already added it at center equal to j. xl, yyzz 0. So what are the ones you're going to iterate through? 0 XOR. Alright, 0 XOR 0 is 0, so we want to go with 0, 1, and 1, 0, right? Well, wait. The second one is 1, 0. So we're going to iterate through. 1 XOR 0 is 1, not is 0. So we're going to iterate through 0, 0, and 1, 1. 0, 0, we should be equal to what? L? No, this should be y z plus equals y z z. Should be like this. Look, that's where I messed up. Okay, why is it still getting wrong answer? YZ plus equals YY. What am I doing wrong still? Also, sorry my explanation was so bad for this. But I don't know. I'm just like not feeling it today, I guess. Oh, YYZZ. YZ. So let's think. This would be 1 XOR. So for 1, 1, we do 1 XOR 1 is 0. Y XOR P. This is 0. This should be 1. Zero, 0, 0. So when we have 0, 0, we should be doing, we're getting the value for B then, right? Because it'd be like 1 XOR 0. Yeah, that sounds right. So what are we doing wrong? Zero, 1, 0. Why is this 0? 3, 0. Oh wait, no, it should be 0, 0. Huh? Why? 3, 0. 3, 0. I, L, 1. Oh, wait. Ugh. Need to add another 2. Ah, this is taking infinite memory. So let's change this to A. Okay. 0. A 1. Zero. Not 1. Well, this should be able to go in here, I guess, right? X or P. Should be this. Uh-oh. What am I missing now? Da, 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 da. 4. Okay, that one's right. Let's try it. Da 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 da. Okay, it's looking right. One more. Moment of oh wait, we need to increase this, of course. Then. Let's go. Okay, this looks promising. The problem is Maxim might be too small, and this amount of memory is not looking good. But we'll try it. Let's see how this goes. Oh, runtime error. Ugh. Too much memory. Okay, so we see our idea was right, but obviously we're like using too much memory. Oh wait, no, that just means... Alright, let's let maximum. How much bigger can we make it? Oh, that's gonna be not good. Will this run? If it runs on ID 1, then maybe it'll run on here. Alright, let's maybe by some miracle this will fit in memory. Oh, it looks like it's working. Let's go, let's go. Accepted. Alright, nice. That was pretty tough. Alright, that was a cool problem. So, basically to summarize, we're storing things in a trie of AI XOR BI. Right, you can see here. Here's where we like traverse the node of AI XOR BI. This means is, this is like a reference to the tree of X, edge Y XOR Z. And then if X is assist, we just return it. Otherwise, we have to set this equal to count, like this global counter, to make a new node. And then here, oh, we could have made this code slightly nicer by doing it like, whatever, I don't care. So here, we're adding the bits when the bits XOR to the same, but they're opposite of both Y and Z, because we'll always add 2 to the J for those. And then for here, we need to add all the bits for the cases when Y XOR Z is different, because that means then we know which is minimum, A or B. So we iterate over the pairs such that the pairs XOR to a different value than Y XOR Z, and then we look at do we XOR with A or B, and we do that for every single bit. Then we have to add for each bit for our pair for both A and B. If the 0 or 1 has a new bit set. I don't know, hopefully that makes a small amount of sense. Alright, wait, let me look at the Kenku. How hard was that one? Oh, nice. Oh, yeah, that was like an orange. Okay, would have been nice to get it in contest, but I like that problem. It was fun. E looks impossible. No, not really. It's not rated that much harder. They're almost the same. Should I look at a tutorial now or think about it more? Well, I'm lazy. Let me just quickly see. Strategy. Maximizing the number of values, not less than B. Okay. Oh well. I'll think about it more first. Well, that's all for today. Hopefully you liked today's stream and today's music. And yeah. Adios, I guess.